Howdy. Welcome back to our video times here in Math 243, Portland Community College, Sylvania campus, Northeast Portland, remote station Utes. We're talking about sampling distribution of a sample proportion. This is the idea that if you take samples from multiple samples from a large population, heck, all the samples that you could take, and you ask the same yes-no question, that proportion of yeses is going to vary from sample to sample. And like sample means are predictable in how they vary from sample to sample, which we learned about in the second section of this chapter. Sample proportions varying from sample to sample are also predictable and can be described using a sampling distribution. Let's talk about some of the details. The statistic, lowercase p, wearing a tiny hat. That's the notation for sample proportion. Statisticians say p hat. I don't like the sound of that, so I say sample proportion p, wearing a tiny hat. Just as the sample mean, x bar, or x with a little bar on top, has a distribution with a mean and standard deviation. And they don't mean just a single mean, the sample mean. They mean samples means varying from sample to sample of the same size. It's really a shortened version of that long sentence, the sample mean. Same thing, sample proportions varying from sample to sample of the same size, or for short, the sample proportion, lowercase p, wearing a tiny hat, also has a distribution with a mean and a standard deviation because proportions vary from sample to sample. What does this distribution of sample proportion p wearing a tiny hat look like? Well, what did the distribution of means look like a couple sections back? Wasn't it kind of, I don't know, unimodal, kind of symmetric maybe? Let's go see what happens. The statistic, sample proportion p with a little hat. Recall from our previous video discussion, or if you're in one of the classes this quarter, we had a Zoom session about it also. The binomial distribution, that describes how many successes we get out of a certain number of attempts if you set the number of attempts and the probability of a so-called success is set to be the same every time. Let x, capital X, be a binomial random variable. X, binomial random variable, corresponds to how many successes out of n random attempts with the same probability. P, wearing that little hat, sample proportion, random variable, corresponds to the proportion of successes out of n random events. Okay, consider the specific case where n is 4 and lowercase p is 3/10, as shown below. This represented, I think it was 4 smokers, each with a 30% chance of developing a severe lung condition in our binomial distribution discussion on a previous video. To get from the binomial distribution, capital X, to the distribution of sample proportions, p, wearing a little hat, statisticians noticed they could just divide all the outcomes by 4. That's it. And the probabilities wouldn't change at all because it's the same basic situation. So the possible values for the sample proportion p with a little hat in this case are 0/4, 1/4, 2/4, 3/4, and 4/4. And the picture is going to look pretty much the same. See that? So the distribution of sample proportions varying from sample to sample, p with a little hat, is going to be exactly the same, identical, to the distribution of a binomial random variable, capital X. This is just a change of scale. Oh gosh, mathematicians and statisticians love simple, so-called simple stuff like that. Kind of complicated to think through, though, for many of us, including some of us mathematicians. Since people just divide by the number n to get from a binomial random variable capital X to the sampling distribution of a sample proportion varying from sample to sample, p with a little hat, statisticians can find the mean and standard deviation of those varying sample proportions, p with a little hat, by starting with the mean and standard deviation of a binomial variable x and dividing by the number of attempts n. See that? They just, down at the bottom of the slide here, you'll notice this very, very not wonderful. You go from number to proportion right here, and all it is just dividing each of the numbers by 4. You can see we drop down into proportions from numbers. That's straightforward. Though I'm saying it's straightforward, we have to really understand the binomial distribution really well for this to feel not complicated. If it's still a new thing and you're still working on your understanding, then yeah, this is another layer of complication on top of that. Division is not easy anyway. Come on, come on. Okay, the mean of the sampling distribution of varying sample proportions, p with a little hat. They just plug in our little idea of dividing to get to the mean mu of sample proportions, p with a little hat. They're saying take the mean mu of a binomial distribution and divide through by n. That's simply, well, n times p was the mean of a binomial distribution. Dividing that by n divides away that number and leaves us with just the population proportion, p, or the probability of a so-called success, p. They actually kind of mean the same thing in some ways. Sorry. It's late. It's like almost midnight. It makes sense to statisticians, especially, and to those of us who have the time and energy to make sense of it, that the center of the distribution of sample proportions, as they vary from sample to sample, should be the true population proportion, or the actual chance of a yes to your question. That's because a good sample should have a sample proportion, near the population proportion from which we've drawn a sample. It says here the sample proportion, that's p with a little hat, is an unbiased estimator of the population proportion. That's just a technical fact that statisticians happen to like. I guess one of them liked it enough to put it on the slide. The standard deviation of varying sample proportions from sample to sample of the same size drawn from a large population, p with a little hat. Well, the notation is sigma subscript p with a little hat, or standard deviation of sample proportions. They're saying take sigma subscript binomial, that's the standard deviation of a binomial distribution, and divide it by that number n, the number of attempts, to shift to proportions. There's the formula, square root of the product of the n, p, and 1 less p as a quantity. Divide that square rooted product by n, and you get back the standard deviation that we want. A little bit of algebraic simplification, if you remember how radicals work, gets you a slightly simpler formula where you only have to write down n once. It's the square root of this quotient of the product of p and the remainder proportion, 1 minus p, with n. Whew. As sample size n increases, you'll notice here the variability in the sample proportion, just like back in the sample mean variability, decreases by the square root of the sample size n. That's because n is under that square root symbol. Back in the second section of this chapter, the standard deviation of sample means, well, you took the population's standard deviation and divided by the square root of n. Fascinating that the increasing predictability of statistics based on sample size has to do with such a simple adjustment by the square root of the sample size. That's fascinating. Okay, like in the previous section about sampling distributions, we have here a description of the sampling distribution, but they didn't give us the picture, so we'll make the picture ourselves. Ooh, let me just also make my screen look nicer for my eyeballs right now. Oh, that's much better. I can see my colors better. Okay, so we'll draw down at the bottom of this slide a bell curve. That's a normal curve. And just so we know what's what, remember that the lowercase p is the population proportion. So I always use red for populations in this like last few chapters of our book. So whenever anything is from the population, it gets a p. And then stuff about samples, I give blue. So here's the mean of all of the sample proportions, mu subscript p with a hat. That's going to be the mean of all the, the mean of sample proportions is equal to the population proportion. That's what that says on the left there. And symbolically, for my picture, I put a red line here and label that with my favorite letter for proportion, little p. So population proportion goes right in the middle of a sampling distribution of varying sample proportions. Then, for the standard deviation, this depends, wait a minute, on this calculation of the standard deviation of sample proportions. That's going to fit into the drawing like this. And it's that funky formula. I can't really fit the formula into my drawing, so I'll just label the standard deviation with its symbol. Standard deviation sigma of sample, that's a p with not a very good tail. Oh my goodness. Okay, let's try that again. P with a little hat. Oh, that's supposed to be a hat. Oh my goodness, my drawing skills have gotten weak tonight. Kind of like that. That's the picture. A normal distribution with a standard deviation given by that formula and a mean given by the population proportion. Again, you'll notice that in the standard deviation, it relates the population parameter, little p, population proportion, with the sample size n. It's that crucial connection between descriptive and inferential statistics given by the central limit theorem. Hooray! Now, how large does the sample size or the number of attempts n need to be for the sampling distribution of varying sample proportions from sample to sample, p with a little hat, need to be approximately normal? That sample size is going to be large enough whenever the expected number of so-called successes and so-called failures are both at least 10. That's if you take the product of n and p, the number, sample size, and the population proportion, if that's 10 or greater, and the product of sample size n and the remaining proportion of the population, 1 minus p, is also 10 or greater. It's a technical thing that is still around from the olden days of statistics. Now here's our practice problem. We're probably going to go do this one over on our class notes so I can do it at human speed and we can keep the notes. It says here, given a population that is exactly half male, so we're in some sci-fi universe with exactly half men, what is the probability that a sample of size 200 would have greater than 55% males? Remember to verify that conditions for normal approximation are met. That's double checking that sample size times that percentage and the remaining percentage are both 10 or more. Let me actually go back into our class and open up our Jamboard for taking notes. I'll pause the video recording to do that. Okay, let's look at how this sampling distribution of a sample proportion plays out to answer a question like this one. Let's take some notes as we go. Given a population that is 50% male, that means that our I'm tired. Our population proportion, lowercase p, is 50%. So that's population proportion. Okay, a sample of size 200, n is 200. What is the probability that a sample of that size would have a sample proportion, so p, I can't type the little hat right on top of the letter p, so I just type it like it's like tipping its hat, like, oh, hello, like this p, and then I type the up caret for the hat. What is the chance that that would be greater than, and you can type greater than or equal to either way, 55%. That's the question. And noting here, whenever you see this, you've got some information here about a population percentage, right? And you've got this question about the probability. What's the probability that a sample, and you got a size, would have, greater than a certain amount? So when you see that kind of a question, the probability that a sample proportion, and proportion because of the percentages, right? That a sample proportion will fall into a range, that's when we're going to use this central limit theorem. So it's that probability about a sample proportion. When we have this question written down here, we're going to use the central limit theorem. Our slides remind us to double check that it's okay to do that. So question about sample proportion in a certain range. Use central limit theorem and sampling distribution of a sampling proportion. Kind of two quick steps to do that. First, we double check sample size is big enough. First, double check sample size, or sample is big enough. So that's n times p being greater than or equal to 10. And also we double check if n times the remaining proportion, 1 minus p, is greater than or equal to 10. Here, our proportion is, you'll notice, 50%. So we only have to check one of those, just 50% of 200. We can just check there, right? So 200 is our n times 50% is 100. So check, good. We got it. And this is the same thing. That's a way bigger than 10. Cool. And then the next thing is to use this central limit theorem. We got to calculate the correct, use the mean. We have to set up a normal distribution with the correct mean and standard deviation. So I'll draw a blue normal distribution to indicate we're in the world of a sampling distribution. I think of samples with a blue pen from back in face-to-face days on Sylvania campus. We know that this is going to have a mean. Straight lines cannot be drawn at this hour with this trackpad, and a standard deviation. They both have their notation. The mean is called, mean mu of sample proportions. So mu subscript p hat, or p wearing a little hat, pardon me, p hat. And the standard deviation is called sigma subscript p wearing its tiny little hat. It's like the letter P went to a little party. It looks like a little pointy party hat. And it's not that bad to get these numbers calculated. The mean mu subscript p wearing a hat, that number is just, I drew it in red because it is the population proportion p, which for us is 50%. Just reminding us that this 50% is the same one back there that lowercase p is that population proportion. The percentage is a proportion. Okay, standard deviation wise, that Greek letter is called sigma, subscript p wearing its little hat. It's got a formula. Now the formula, let me write it out up at the top of the slide so you can see it better. The formula for the standard deviation sigma of sample proportions p wearing their little hat, what you do is you take the population proportion, that's a red p in our notation here, and you multiply it by the remaining proportion of the population, 1 minus that population proportion p, divide that product by the sample size n, and take the square root of that entire quotient, like that. Now, typing that up, because I'm a nerd, I like to type my stuff the way a computer can read it. So I type SQRT and parentheses for that square root symbol. So squirt, SQRT is square root in computer ease. And then I type in here P times 1 minus P divide N. And I can just plug in our numbers that we have over there in our work. P is 50% times, well, 1 minus 50% is 50%. Divide that by sample size 200, and we'll have our standard deviation. I'm just going to copy that. I'm going to a different window where I've got a calculator, and I get a number that I'll copy and paste for you. 0.3535533905. I just like reading all the numbers. I'll round that off to 0.536. Well, maybe 0.534. I'll go, maybe 0.35. That's a nice round off. It's 2 digits of accuracy for my notes isn't so bad. So that's going to be our standard deviation. Notes-wise, this is the number that goes on that little arrow up there in our graph. Now, knowing that 3.5% is the standard deviation, so that'll take me from 50% here, that'll be like 58.5%, sorry, 53.5%. 2 standard deviations would be about 58%. So somewhere like there, somewhere like right there is going to be 55%. And our goal, like on this scale, because that standard deviation is 3.5%, we got to get a little more than 1 standard deviation up there. And our goal, that probability, you'll notice I underlined probability in green. We want to find this area up here under this curve, and that will get us our result. Okay, that we can do now in GeoGebra, because we have our mean written down, 50%, our standard deviation, 3.5%, rounded to the nearest, half or 1/10 of a percent, and we've got our likelihood defined, the probability that a sample proportion P with a little hat is above 55%, as in this drawing. Calculating in GeoGebra, let's go do it. And just for my notes, calculating using GeoGebra normal distribution. We'll get Px, because that's what it's called in GeoGebra, greater than or equal to 55% is how we'll enter it over there. We'll go get our result. Let's do it. GeoGebra.org/classic #probability. Here we go. We'll see this normal curve arise in our desktop. I can remember my mean is 50% or 0.50 for half male. I can remember the standard deviation because I think I just cut and pasted it is, oh, I just pasted it again and I got it back. I got an accurate standard deviation, 0.35, and then lots more digits. I just held on to them because I had it in my pasting ability on my computer. We're going to look above, so I'll grab the right-sided bracket down there at the bottom of the screen. Above 55%. Hey, that looks pretty good. Remember my little drawing back in our class notes? See my little green area at 55% and up? I got to admit, I love drawing little bells, and it kind of shows. Hey, yeah, that's 0.786 is the probability of ending up with a sample of 200 members of this population of half men with 55% or more men in it. Let's write down that conclusion. 0.786. Did I remember that number? Yeah, I did. And hey, let's take a screenshot of the GeoGebra calculation while we're here. Let's put me in the screenshot to see if it does it capture me from Zoom. Let's find out. I'm just curious. Does the Zoom window show up in a screenshot? Let's find out. I'll make a funny face. All right. We'll find out. I'm going to save this screenshot in our class notes. Maybe in our class notes or maybe on our slideshow. I'll decide after I finish the video. Yeah, let's head back to here and just put our conclusion. There's about a 7.7% chance, just rounding off that result, of finding a sample of 200 people with greater than 55% men. I muted myself at some point by accident, and I have no idea when I did that. I hope that just happened. I'm just writing up the conclusion. I'll double check this video when it's done. That's really how we do these problems. The crucial steps here are once you recognize that you're in this situation, probability, a question about a sample proportion, a question about a sample proportion falling in a certain range. We can use the central limit theorem, which gets us to this probability distribution, and there's this crucial step of adjusting and finding both the mean and standard deviation. Why is this happening? What is going on? Am I getting recorded? Something weird is happening to my computer here. A cat has invaded the space. Psst, you, get down from this table. Buddy, I'm not kidding. Get down. Psst, get down. Good boy. Okay, it's like almost midnight. I'm doing a bad job trying to be awake when it's after my awakeness time. I hope this example made some sense, and when you're all done, you end up at that point able to talk about how likely it is to find a sample proportion in a certain range. Crucial steps: getting the mean and standard deviation correct once you're confident the sample is big enough for this method to work. We will see this sampling distribution of a sample proportion again when we move forward into Chapter 5 and study statistical inference techniques for calculating margins of error for confidence intervals which estimate population proportions. And we'll also learn how to do hypothesis tests where we make an assumption about a proportion in a population and see how likely sample data looks compared to that assumption. In both cases, the underlying mathematics will be done using this sampling distribution. So there you go. Not the deepest video on this topic, and I'm sure you'll have questions. So bring those questions either to our next Zoom session if you're a Zoom session attendee, or contact me and let me know what your question is, either in one-on-one support time or using any other method of contact. All right, I'm gonna go try to get some sleep and go learn some stuff at a conference this week. I'll try to stay in contact and do my best to keep up with y'all. Also, yeah, get any more feedback that you deserve. Okay, have a good one. Good night.